All right, let's jump right into this explainer. Today, we're initiating a full system diagnostic on the massive, complex machine that dictates literally every day of our lives, Earth's atmosphere. You know, when someone asks you what the weather is like, they're really just asking for a real-time status report on this vast, invisible engine. So we're going to break down the pure mechanics of meteorology to understand exactly how this whole extraordinary system operates.
Here's the agenda for today's explainer. 1. Our atmospheric engine. 2. Fueling the heat budget. 3. Atmospheric water and clouds. 4. Air masses and fronts. And finally, 5. System overdrive, severe weather.
Section 1. Our atmospheric engine. The chassis of the atmosphere. Okay, let's start with the raw materials that make up the invisible engine we all live inside. Nitrogen and oxygen make up 99% of the planet's atmosphere. 99%! But the really fascinating part? All the dynamic weather we experience exists almost entirely because of that tiny 1% of trace gases. We're talking things like water vapor, carbon dioxide, and ozone. Without that tiny fraction, our planet would just be a lifeless rock in space.
Our engine also has these very distinct vertical layers. The troposphere is that lowest layer, and that's where the chaotic mixing of weather happens. Down here, the temperature drops as your altitude goes up, which creates a highly unstable environment where warm air is constantly trying to rise while cool air sinks. Then, right above that, we have the stratosphere. Think of this as a stable, ozone-rich shield that absorbs high-energy UV radiation from the sun, protecting all that chaotic weather below.
Moving on to Section 2, fueling the heat budget, solar energy, and thermodynamics.
So, every engine needs fuel, right? And for our atmosphere, that fuel is entirely dictated by incoming solar energy and the strict laws of thermodynamics. Which brings us to a critical question. How exactly does our planet avoid completely overheating while it's constantly bombarded by intense solar radiation? The Earth is always trying to maintain a strict energy balance. If it only absorbed energy, the whole engine would eventually boil over. Well, a big piece of that puzzle is albedo. Albedo is basically a measure of reflectivity. Highly reflective surfaces, think vast fields of snow and sea ice, actually bounce a significant percentage of that raw incoming solar fuel right back into the void of space before it can even be absorbed by the surface. But what about the energy that does make it through? That's where the greenhouse effect steps in, as a crucial insulator. Incoming visible and UV light passes right through the atmosphere. The surface absorbs it, converts it to heat, and then tries to radiate that heat back out as thermal infrared radiation. But our greenhouse gases actually trap a portion of it. This insulation is exactly what keeps our atmospheric engine running at a comfortable, habitable temperature, instead of just freezing solid the second the sun goes down. Section 3. Atmospheric water and clouds, the coolant and hydraulics. Let's look at the hydraulics of our system, where water transitions between invisible vapor and visible clouds to transport massive amounts of heat. It starts with humidity. Now, warm air can hold more water vapor than cool air. So, when our atmospheric engine cools down to a specific threshold known as its dew point, the air suddenly reaches 100% humidity. At this exact point, all that invisible water vapor is forced to condense around microscopic particles and turn into a visible liquid state. And when it comes to those clouds, they're categorized primarily by their altitude and their potential to make rain. And hey, fun fact for you, even though they look like weightless cotton candy, a single cumulus cloud can actually weigh as much as 100 elephants. High up, you've got wispy ice crystal cirrus clouds. In the middle, alto clouds. Down low, water-heavy stratus clouds. And spanning across multiple levels are the nimboform clouds. Those are the thick, active ones responsible for the vast majority of our precipitation. You know what's fascinating? Fog is really just a cloud operating at ground level, and it's classified by the precise physical mechanism that cools the air below its dew point. Radiation fog forms as the ground cools on clear nights. Advection fog, like you see blanketing San Francisco, rolls in when warm moist air blows over a cold ocean current. Steam fog rises off warm autumn lakes. And upslope fog forms when humid air is mechanically forced right up the side of a mountain. Section 4. Air masses and fronts, the moving pistons.
Now we're getting into the mechanical pistons that actually drive our daily weather forecasts. Massive blocks of air and the turbulent boundaries or fronts between them. An air mass is a huge body of air with uniform temperature and moisture. When a cold air mass attacks a warmer one, you get a cold front. Since cold air is denser, it acts like a giant wedge, aggressively scraping along the ground and violently pushing the lighter warm air up into the upper atmosphere. That sudden, unstable lifting is exactly what triggers towering cumulonimbus clouds and those sudden, violent thunderstorms.
On the flip side, when a warm air mass replaces a cold one, we get a warm front. This is a much slower, gentler mechanical process. The warmer, less dense air advances by basically riding gently up and over the heavier cold air mass. Because this lift is so gradual, it produces vast, flat stratus clouds and extended periods of mild, steady rain.
But sometimes, these massive moving pistons just lock up. When two contrasting air masses collide in a stubborn stalemate, neither has the momentum to budge the other. We call this a stationary front. The boundary stalls out over a region, often dropping continuous, mild rain for days on end, as the atmosphere just waits for a shift in equilibrium to break the tie.
Now, when the engine really revs up, a rapidly moving cold front can actually completely overtake a warm front. This creates an occluded front. The warm air gets completely squeezed and forced right off the ground, wedged up between two colder masses of air. The weather right at this occlusion point gets incredibly fierce, bringing heavy precipitation and rapidly shifting winds.
Section 5. System Overdrive. Severe Weather. Equilibrium through Chaos.
So, what happens when this engine is pushed to its absolute thermodynamic limits to balance out extreme temperatures and moisture? Well, every individual thunderstorm, no matter how severe, follows a strict three-step life cycle. First, in the cumulus stage, warm updrafts build the cloud. In the mature stage, heavy rain creates cool downdrafts that coexist with the updrafts. That's where you get intense winds and lightning. Finally, in the dissipating stage, those cool downdrafts spread out and completely choke off the warm air fueling the storm. Basically, the storm starves itself.
But throw in the right conditions of extreme instability, like intense surface heating and wind shear, and things get much more dangerous. Those atmospheric updrafts can begin to twist into a rapidly rotating vertical column called a mesocyclone. It's right from this tightening, spinning core inside a supercell thunderstorm that the devastating funnel of a tornado can descend to the ground.
Out over the tropical oceans, our engine taps into an even larger source of power. Massive amounts of water evaporate and then condense high up in the atmosphere. This phase change releases something called latent heat. And latent heat acts exactly like a massive continuously charging battery. It provides the immense thermal energy required to rapidly spin up a hurricane.
Looking at the anatomy of a hurricane, there's a wild paradox. The storm starts out as a tropical depression, building around a central low pressure. But once it's fully formed, the central eye of the storm remains eerily, almost unsettlingly calm. But step just outside that calm and you hit the eye wall. That's a towering ring of cumulonimbus clouds containing the absolute lowest atmospheric pressure and the most catastrophic winds on the Saffir-Simpson scale. It's not just about tropical moisture, though. Take a winter blizzard. It's actually not defined by the cold, but by the sheer kinetic force of winds exceeding 35 miles per hour, combining with blowing snow to completely blind visibility. On the exact opposite end, a heat wave is formed by a stagnant, high-pressure lid in the upper atmosphere that just traps heat down at the surface for days. Whether it's the kinetic fury of a blizzard or the suffocating blanket of a heat wave, these extremes are just the atmosphere desperately trying to return to equilibrium. Which brings us to a final, pretty critical question for this explainer. The scientific consensus is clear here. Human activity is rapidly altering the composition of those highly sensitive trace greenhouse gases we talked about at the very beginning. As we continuously inject more heat-trapping gases into this finely tuned machine, throwing the heat budget out of whack, just how volatile will this atmospheric engine become in its search for balance? It's a question of mechanics, of thermodynamics, and ultimately, it's a question of our future.